So first, let's talk about the derivative. We know that the derivative was associated with the rate of change. So we have a function, the derivative was associated with the slope of the tangent line and the rate of change of how the function was behaving with respect to the time. Now, an obvious question is, well, if antiderivatives are reversing that operation, what is the meaning, what is the geometrical meaning of having an antiderivative? So for that, let's consider that we have a moving object about a line, okay? And the slope of the tangent line is going to give you the velocity at that time. Now, if we turn the situation around, what happens if we have the velocity of a moving object? Can we obtain the position? Well, the idea of the antiderivative tells me that yes, but then what will be the meaning of it? So consider now a car that is traveling to a constant velocity of 60 miles per hour in along a straight highway over like a 2 hours period. So we have here the graph of that. We have the 2 hours period, and we have the speed function, which is a constant function. Notice that the graph of the velocity function on this interval is a horizontal line. Now, the product of this is this area of the rectangle formed by the velocity curve and the axis between 0 and 2. So in this case, we see that the area below the velocity curve and that the axis is going to actually be the displacement. And that makes sense because if you remember, distance is speed by time. And so if we multiply the speed by the time, we're going to get the distance. So in here, if we're multiplying the speed by time, we're going to get how much distance is covered, which in this case is going to be 120 miles. Now, this is an easy case because we have a constant situation, so we can approximate this area with just the area of a square or the area of a parallelogram, really. But if we don't have something that is constant, then this is going to be a little bit more complex to figure out. But we can conclude that the meaning of the integral or the antiderivative is just really going to be the area below the curve. So how much is being covered by this? Now, suppose that we have the velocity of an object in terms of meter by second and it's moving along a line given by a different function. This time we're going to take the function t squared between t with t moving between 0 and 8. Now, we want to approximate the displacement of the object by dividing the interval of 0 to 8 into n subintervals of equal length. In each of the subintervals, we're going to approximate the velocity by a constant equals to the value of b evaluated at the midpoint of the subinterval. So notice this is my curve. This is t squared. And so what we do is we're going to approximate by dividing this into squares that we can use to approximate the area. And the height of those squares, or the height of those parallelograms, is going to be given by the middle point. So for example, for this, when n is equals 2, I'm going to go from 0 to 4, and then from 4 to 8. And the middle point is going to be 2, and it's going to be 6. So that's going to give us the height of the parallelogram that we're going to use to approximate. Now, in this case, you can see that's going to generate some issues. This is not a good approximation of the area below the curve. There's spaces not taken into account here, spaces that are above the area here, similarly here. So we are not really very precise. Now, if we continue dividing in more subintervals, let's say from 0 to 2, 2 to 4, 4 to 6, and 6 to 8, then you notice that the approximation is going to get a little bit better. Notice that now we have parallelograms that are thinner, and the approximation doesn't leave many things extra. So if we're approximating this piece of the area, this piece that is left that we don't need, probably approximates the area here. Similar, this part is going to approximate this piece here, and this piece is going to approximate this piece here. So overall, it's a really good approximation in this case. Okay. Now, if we go further and we approximate with much more intervals, then you notice that every time the mistakes that I'm doing are smaller and smaller, and probably this is going to be much more closer to whatever the area under the curve for this is going to be. Now, if we extrapolate this a lot, and now we do 64 partitions, we're going to get 64 small parallelograms here, or rectangles. And with those we can calculate the area, and then after adding up all this here, then we're going to have a good approximation to what the area under the curve is. Now we want to use that procedure, and then we're going to calculate the area. And so notice what happens when we take a look at each of the approximations. So we have t squared on 0 to 8, and the number of subintervals is going to give me a better approximation of the area under the curve. Notice with one subinterval, the length of the subinterval is 8, and the area under the curve is 128, which is probably not very reliable. Now when we jump to 4, the length of the subinterval is 2, and it's 168. And when we get to, let's say, 32, the length of this interval is smaller, 0.25, but we're getting to 176.25. And you can see that in the next iteration, when we're coming to 64 subintervals, the difference between the areas between this and this is not that large, and we're closely approximating a number that we can concisely call the area under the curve. So if we go for the limit, very likely we're going to get a pretty good approximation of that area. Now, in general, consider a function that is going to be continuous and not negative on the interval a, b. The goal here is going to be approximate the area of the region bounded by the graph and the x-axis here in the interval a and b. Okay, so we want to approximate this area. So what we're going to do is going to be something similar to what I just showed you. We're going to divide that interval a to b in smaller subintervals, x0 to x1, x1 to x2, xn minus 1 to xn. Well, of course, x0 is going to be equals a, and xn is going to be equals b. Now, the length of each of the subintervals, so how much is going to measure, is going to be denoted by delta x. And that's going to be found by dividing b minus 8 divided by n, where n is the number of subintervals that we're taking. So something more or less like this. We'll start from a up to b, but we're moving delta x distance every time that we're trying to get a new value. Now, once that we have that notion, then we can define what it is. And it turns out that this is going to be called a regular partition. So in an interval AB, if I take this division of a smaller subintervals where they have equal length, delta x equals b minus a over n, and the starting point and end points are the initial and end point of the sequence, then those subintervals are going to be called grid points. and they're going to create something that is called a regular partition. In general, you can just always find the xk element by doing the initial number a plus k times the delta x, since this is a fixed amount of distance. Now, with this into account, then we can more easily approximate what's going to be the area under the curve. Notice we're taking certain values x1 star to determine where the height of my rectangle is going to be. If I take x1 star, then f of x1 star is going to be this height, f of x2 star is going to be this one, f of x3 star is going to be this one, and so on. Okay. Now at this point, notice that what I'm going to do is I'm going to approximate by using the areas of the rectangle. So of course, the area of the key rectangle is just going to be the height times the base. And the height is given by f of that given point that we pick. And the base is just going to be delta x, which we know because it's b minus a over n. Now at this point, we can define what this is going to be, and we call it a Riemann sum. So suppose that you're in interval close AB, which is divided in subintervals of length delta x. If you have that xk star is any point on the subinterval xk minus 1 to xk, then you can represent the Riemann sum, or the area under the curve, as f of x1 star delta x plus f of x2 star delta x plus f of x and delta x. And this is going to be called the Riemann sum. And now, depending on where the point is, this x1 star can be to the left of the interval, in the right side of the interval, or the middle point of the interval. And so depending on that, we're going to have a left, right, or midpoint Riemann sums. Okay, so the first is the left Riemann sum. So what happens here? In our partition, notice that we're always going to consider or point for the height to be the left side of the partition. So notice here, for this particular Riemann sum, we're taking the height of the left end of each of the partition intervals. So here we're taking x1a, and the height of the first rectangle is given by that point. Then we're gonna have x2 to be x2 star, and that's going to be the height of the second rectangle. Similarly here, x3 is going to be the height of the third rectangle, and so on. So in general, for any given interval, a left Riemann sum is going to always take the height that produces plugging the left side of that interval into the function. Now, the right Riemann sum, by obvious reason, is going to be developed in the same way, but now we're going to take the endpoint of each of the subintervals. So we're taking the right side as the point for creating the height of these rectangles. So notice in comparison, here we were taking the left side, now here we're taking the right side to produce the height. Of course, we have one more case, which is where we take the middle to create the height of these subintervals. And depending on what we do and which one of this we're taking, then the results are going to vary a little bit more or a little bit less, depending on the error that is produced for each of these approximations. Now, let's take a look at one example of doing this. Consider R to be the region bounded by the graph of 3 square root of x, and the x-axis between x equals 4 and x equals 16. Now, we're going to consider a left Riemann sum. So we're going from x equals 4 to x equals 16. and we're going to split here every two digits. So delta x is going to be 2. And as you can see, we go from 4 to 6, from 6 to 8, from 8 to 10, 10 to 12, 12 to 14, and 14 to 16. Since we're taking the left Riemann sum, then the height is always going to be given by the left part of the interval. So here for the first rectangle, we're going to have the height given by f of 4. Here we're going to have the height given by f of 6. Here we're going to have the height given by f of 8, f of 10, f of 12, and f of 14. Notice that there's, of course, one number that is not going to be covered. 16 is not going to be covered because the left side of the interval 14 to 16 is already given by f of 14. But if we do this partition with the right Riemann sum, the opposite is going to occur. In here, we're not going to take the value of 4, and instead, the first subinterval is going to be given by f of 6, then f of 8, f of 10, f of 12, f of 14, and in this case, we are taking f of 16. So that's going to produce the height of each of these intervals. Finally, the midpoint Riemann sum is going to take the midpoint between each of this interval. So for example, for the first interval, which is between 4 and 6, we're going to take 5. And so f of 5 is going to be the height of this rectangle. F of 7 is going to be the height of the next, f of 9 the next, f of 11 the next, f of 13 of the next, and f of 15 for the next. The length of all this is always 2, but it varies by the height. Okay, so all this, they produce different approximation. Notice here that we seem to be having, we seem to be lacking, and it's an under approximation. In the right side, we seem to have an over approximation where we're having things that are extra on our approximation. And the midpoint Riemann sum seems to be very close to what it should be. If we take into account that the extras should account for what is not being covered. Now, there are a couple more things that we're going to get once that we organize this. We have to add them up, right? And so notice that if we're adding this up, then one of the things that's going to happen is that the sum is going to be one of the factors that we need to take into account. So in a Riemann sum, let's say that this is the right Riemann sum, and we can also write the left Riemann sum. Okay, so for the right Riemann sum, notice that we're taking f of 6. So f of 6 is the height of the first interval times 2, which is the delta x, plus f of 8 times the delta x, which is 2. So notice this is the area of this whole rectangle. This is the area of this whole rectangle. Now f of 10 by 2 is going to be the area of this rectangle here, plus f of 12 times 2 and f of 14 times 2. So with this, we have the sum of all the 6 subintervals. Okay. In case of the left Riemann sum, we're going to have f of 4 by 2 plus f of 6 by 2 plus f of 8 by 2 plus f of 10 by 2, and so on. F of 12 by 2 and I'm missing f of 16 on this one. Okay, so this is how it looks when we're calculating this area. Of course, in this case, it's just 6, so it's not a big deal to make each of the cases. I can even do the middle Riemann sum. So I can go f of 5 by 2, f of 7 by 2, f of 9 by 2, f of 11 by 2, f of 13 by 2, and f of 15 by 2. And so that's going to cover all the possible approximations. Now, when this is larger, when we have a larger partition, it's a little bit more cumbersome to approximate, but this is the overall idea. Each of these pieces is giving me the area of a particular rectangle. Now, we're going to use some notation for the cases where we can just take this and make it larger. So for example, if I can just write all these things in notation sum, I can just write this is the sum from I equals 1 to 6 of f of x I star times 2 delta x. And remember, the delta x is 2, f of x1 is 6, f of x x2 is 8, x3 is 10, x4 is 12, x5 is 14, x6 is 16, at least in this case. And of course, on this side, we could also use this type of notation from 0 to 5 of f of x I star delta x, and so on. So in general, notice that this is a sum. We can establish this as a sum, and we can be talking about what is the sum from I equals 1 to n of f of x I by delta x. Okay, so this is what we want to know. This is what we want to know what's going to be happening there. So for that, we need this this particular expressions, which are the powers, the sum of powers of integers for certain special values. So if we sum the constant c n times, we're obviously going to have n times c. And so this is the easiest of everything. But now, if we have the sum from the first n numbers, so 1 plus 2 plus 3 plus 4 plus 5 plus n, then this can be summarized as n times n plus 1 over 2. Now the first n squares is going to be given by n minus n plus 1 times 2n plus 1 over 6, and the sum of the first n cubes is going to be given by n squared times n plus 1 squared divided by 4. Now let's take a look at an example of how that will influence our Riemann sums. So we can describe our left, right, and midpoint Riemann sums using this sigma notation. So as I was showing you before, we established first this k equals 1 to n of f of x k star delta x. And depending if we're left, right, or midpoint Riemann sum, then we can just find out how to describe our points. So for example, for the left Riemann sum, xk is always the initial point 8 plus k minus 1 delta x. On the right Riemann sum is xk star is going to be 8 plus k times delta x. And the middle point Riemann sum, xk star is going to be 8 plus k minus 1 half delta x. Now, one proper example of this will be taking the function x cubed plus 1 between 0 and 2, and let's approximate using fictive subintervals. And let's check what the curve is going to do. Notice f of x equals x cubed plus 1 is our functions, and so we're going to split this in fictive subintervals. Notice that the length of each of the subintervals is going to be given by delta x, And so delta x here is b minus a over n, so 2 minus 0 divided by 50, or 1 over 25, or 0.04. So it's a very small delta x, it's a very small distance between each of the subintervals. Now for the left Riemann sum, we can find out then what our xk is going to be. A is 0, and then we have that the delta x is 0.04. So that's going to mean that our xk star is going to be 0.04k minus 0.04. For the left Riemann sum to be evaluated, then we plug that in the function on this Riemann sum formula. And so we do f of that xk multiplied by delta x, and then we analyze how much that's going to produce. So here we're going to get that that's going to be around 5.8416 after doing a lot of computations. If we evaluate the right Riemann sum, then we're going to get that x is equals a plus k delta x, and that's going to be equals to 0.04k. And if we approximate that, that's going to be 6.16, and so on. And we can do the same thing for the mid-Riemann sum. So we calculate what the initial point is, then we multiply by the delta this, and then this is going to be plugged in the function, and then we're going to use that function in each of this case, and we're going to add up what the value of the function is, and we're going to get that this is 5.99. So as you can see, this table is going to show how the left, right, and midpoint Riemann sum are going to work up to 200 values. So as you can see, the closer that we get to higher values, this numbers start to get really close. When we're getting to the 200 number, you notice that the left Riemann sum is 5.9, right Riemann sum is 6.0, and the middle Riemann sum is 5.99. So you start to get really close with all the approximations. Now, I know that I didn't do the calculations in here, and so that's going to be the topic of part 2 of this section. Okay, so in part 2, I'll see you where I can show you some more concrete examples of how to calculate this Riemann sum with some easier partitions to calculate, not 50, but let's say 5 or 4. And then check what is the left and the right Riemann sum. So see you in part 2.